Good day everyone! Today we'll be talking about matrices and how to use them in solving linear equations. We'll be discussing three different ways to do this. The first would be matrix inverse, followed by Cramer's rule, followed by Gaussian elimination. First, let us discuss the matrix inverse. The matrix inverse is basically the equivalent of a reciprocal for a matrix, meaning if you were to multiply the matrix by its inverse, it would result in the identity matrix. A matrix may have an inverse if and only if its determinant is not equal to 0. The formula for a system of linear equations is as follows. A represents the coefficient matrix, X represents the variable matrix, and B represents a constant matrix. Let us consider the following system of equations. Matrix A contains the coefficients of the variables in that system. Matrix X contains the two variables used in this system, X and Y. Matrix B contains all the constants in the system of equations contained in the right-hand side. To solve for the values of the variables X and Y, we can make use of the matrix inverse. Since there is no such thing as division in matrices, the closest we have is matrix inverse, and the formula goes as follows. Now let's try to solve the following example. First, let us derive A, X, and B. As you can see, matrix A contains the coefficients of X and Y, matrix X contains the variables X and Y, and matrix B contains the constants 5 and 7. Using this handy little formula for a 2x2 matrix, we can solve for the inverse of matrix A and thus solve the system. Now we can substitute the matrix inverse of A into the following formula and get the variable matrix. We multiply the matrix inverse of A and the coefficient matrix to get the values of X and Y. From this, we solve that X is equal to -1 and Y is equal to 1. Next, let us discuss Cramer's rule. Given the following system, we can create matrix A, which is a matrix of coefficients. As you can see, in the first column are all the coefficients of X, in the second, the coefficients of Y, and in the third, the coefficients of Z. In order to solve for the variable you are looking for, you would need to create a new matrix by substituting the constants into the column which represents the coefficients of the variable you are looking for. For example, if I were to be looking for X, I would substitute the constants into the first column. If I were looking for Y, I'd substitute it into the second, and if I were looking for Z, I would substitute it into the third. To solve for the value of a single variable, you merely need to divide the determinant of your new matrix by the determinant of your original matrix, and the formula goes as follows. Let's try the following example. Miko has a total of 12 chickens and cows, and he counted 34 feet, but he's not quite sure how many chickens and cows there are. In order to solve for the number of chickens and the number of cows, let's consider the following. Let X be the number of chickens and Y the number of cows. From the following system of linear equations, we can get the following matrices and their determinants. As such, we solve that Miko has 7 chickens and 5 cows. Lastly, let us discuss Gaussian elimination. In Gaussian elimination, we have to turn the following system of linear equations into what's known as an augmented matrix equation. To do this, we need to augment the matrix containing the coefficients of the variables and the matrix containing the constants. Next, we need to find a way to turn the matrix of coefficients into a triangle matrix, either an upper or lower one. To do this, we make use of what's known as row operations. First, we can subtract the corresponding values of the first row from the second row. Next, we can multiply the values of the first rows by 3 and subtract them from their corresponding values in the third row. Lastly, we can subtract the corresponding values of the second row from the third row. Now that all the values that we need to be 0 are currently 0, we can turn the matrix into a system of linear equations that is much easier to solve. But you can keep going and turn the matrix into what's known as its echelon form. In the echelon form, you're creating an identity matrix from the coefficient matrix. From this, we get the following: x equals 0.3, y equals 0.4, and z equals 0. That's all for today. Thanks for watching.